Okay, so in this problem we are asked for the rate constant for a reaction. This is the reaction we're looking at, and we're given a table of data. This is the general setup for something that involves the method of initial rates. So we're going to be using the differential rate law. And so I'm going to go ahead and start by writing that out. So the differential rate law, remember, is just that we set the rate equal to k, the rate constant, which is ultimately what we're going to try and solve for here, and we take the concentration of the reactants and multiply them together. And we raise them to different exponents. Those are called the orders, or the order of the reagent or reactant for the particular reaction. So what's the order of A? It's going to be X, order of B is going to be Y, and the order of C is going to be Z. So we can solve this equation for k using the data in this table, but first we need to figure out what x, y, and z are. And so this problem is a little bit of a pain because of the way that the experiment is set up. But let's take a look. So the first part, let's start with just looking at A. So we're going to solve A. We're trying to find what x is. And we can come down here and we can look for places where B and C are held constant, but A is not. So if we look at experiment 1 and experiment 3, we see that B and C are held constant, but the concentration of A has changed. And that is how you would want to set this experiment up, because it allows us to see exactly how changing the concentration of A affects the rate of the reaction. That's essentially what we're talking about when we talk about the order of the reaction in A. So then we can just go ahead and solve this. We take the ratio of the concentrations and set them equal to the ratio of the rates. And what we see is that we have this equation 4 to the x is equal to 16, and we can just solve that by inspection. And we see that x is equal to 2. So what this tells us is that whatever we do to the concentration, like if we change the concentration in some way, the rate is going to change as the square of that. So here we change the concentration by a multiple of 4. How does the rate change? It goes up as a multiple of 16. So if I take 0.1 and multiply it times 4 to get 0.4, what I know the effect on the rate would be is that would mean that I would take the rate here and I would multiply it times 16 to get this rate down here. So this is important for solving the rest of the problem. Because the way this experiment was set up, they didn't do a good job of isolating their variables. So now let's say that we're going to try and solve for the order of B. So what we do is we come and we try and look for places where A is constant and C is constant, and that will allow us to see the effect of B on the rate of the reaction. But for some reason, the person performing this experiment did not set it up in such a way that it makes it easy to isolate out, so we have to do a little bit of extra work. So if we look at, let's say, going from experiment 2 to experiment 4, C is held constant. So we know that whatever the change in the rate is over here is not affected by C. But A is not held constant. And what we're trying to see is what the effect of changing B is on the rate. And so as it is, we don't know, we can see the rate is changing as I go from experiment 2 to experiment 4, but I don't know if the effect is coming from B or A, because both of these are changing. So I haven't isolated out this variable. So the experimentalist should have kept this constant at 0.1, but did not for whatever reason. But because we know the order of A, we can go ahead and back out the effect of A from the rate change. So we know that by doubling this, it's going to have a particular effect on the rate, and we can kind of get rid of that and sort of introduce like a correction factor here. So first, let's start by looking at the contribution of A. So the contribution of A to the rate is going to be related to the change in the concentration. And we can just say that, well, if we go from experiment 4 to experiment 2, we know that the effect on the rate is going to be the square of whatever that change is. And so it's 0.1 divided by 0.2 divided by 0.1, so we end up with 2 squared, and so we end up with 4 there. So the contribution of A, or the effect of A on the rate, is multiplying it times 4. So what I'm saying is, as I double this, I know that the contribution it's going to have on the rate is it's going to quadruple the rate. So what we can do is, so that we can actually isolate out B here, is we can just divide the rate that we see from experiment 4. So I'm taking this rate from experiment 4 here. I'm just going to divide it by this factor of 4. And what do I get? I get 5.2 times 10 to the minus 3. And I should be careful with my units here. Like a good instructor. Okay, so this rate then is sort of like a corrected rate. And now we can figure out what the order of B is. So now we just solve it like normal, but instead of using the data from the table for the rate for experiment 4, we use this new data, or this new kind of tabulated value that we calculated over here, that corrects for the fact that A was changing. And so we can take this and we can say, okay, well, we take the concentration. So now I'm working at the actual order of the reaction here. So I take the concentration of B, and I divide it by the concentration. I take the concentration B from experiment 4 and I divide it by the concentration of B from experiment 2. I set it to the power of y, and I set that equal to the rate from experiment 4 that we corrected. We can leave the units off because we're dividing. Divided by the rate from experiment 2. And now we just solve for y. So 0.8 divided by 0.3 gives me 2.66 raised to the y power. And then if we take 5.2 times 10 to the minus third and divide it by 1.95 times 10 to the minus third, we also get 2.66. So what's the order in B? It's just first order in B. So what it means for something to be first order is that whatever multiple I change the concentration by, that means that the rate will change by that exact same multiple. So for example here, this is sort of a weird one because I'm going 2.6, but I changed the concentration from 0.3 to 0.8, I multiplied it times 2.66. And then what effect did that have on the rate? Well, the rate also changed by 2.66. So that's what it means for something to be first order. And so now we know it's first order in B, and we can finally go and look at C. Okay, so how are we going to go ahead and do that? We end up in the same problem where we note there is nowhere, if you come and look over here, there's nowhere where A and B are held constant, but C is changing. So we can go ahead and look at, let's look here. So at least here, yeah, let's just go ahead. We can look at, we can look at this one. So A is held constant as we go from here to here, so we don't have to worry about that. B is not, so we're going to have to correct for that. And then C is doubled, so we can try and figure out what the effect is on the rate. But we have to, again, do this correction here because B is changing. So we do the same thing here. So what's the contribution from C to the rate? That's what we're trying to correct for. I'm sorry, the concentration of B. What's the contribution to the change in the rate for that? Well, we do the same thing. We say, okay, well, we're going from 0.3 to 0.2, or 0.2 to 0.3 as we go from experiment 1 to experiment 2, and we divide those. Of course, this is raised to the first power because, we're looking at a first order reaction. And so we know that the rate here, the contribution to the rate as we increase, as we go from experiment 1 to experiment 2, it's just that it's been multiplied by 1.5. That is what B is contributing there. So we can get rid of that and again do this sort of corrected rate. So we'll take 1.95 times 10 to the minus 3, and we will divide it by 1.5. And this will give us our new rate, which is 1.3 times 10 to the minus 3 moles inverse seconds. And then we can go ahead and solve finally for what C is. So this one is straightforward because we see that the rate doesn't change. So in experiment 1 it was 1.3 times 10 to the minus 3. In experiment 2 corrected, call it like experiment 2 corrected is a way to kind of think about it. We see that it's exactly the same, 1.3 times 10 to the minus 3, so it hasn't changed at all. So what's the order of the reaction in C? We don't even have to do any kind of calculations. The E is just going to be equal to 0. It has no effect. So that's what it means for something to be 0 order. I double the concentration. It has absolutely no effect on the rate of the reaction. So if I quadrupled it, what do we expect the effect to be? Again, it shouldn't have any effect. So it's 0 order in C. So then we can come back up here and finish out solving what we wanted to here. So we know that this then simplifies to k times a to the second power times b to the first power. And now we can just solve this to find the rate constant. So we can solve for k. We can say that k is equal to the rate of the reaction divided by the concentration of a squared times the concentration of b. And I can just pick any of this data here and work this out. So I'm just going to choose the first one at the top here. So I've got A, and I have B. C I don't even care about because it's not, it's 0 order. And then I also have a rate here which I can plug in right there. And so I can do that. So I take the rate and I divide it by, probably it makes sense to start adding in concentration units and stop using the brackets at this point. And I end up with this expression, which if I simplify, I end up with 6.5 times 10 to the minus 2. It's probably smarter to write that out. It's just 0.65. And then our units end up being, let's see, so this cancels out with this. And so I end up with these sort of weird units of inverse molar squared. I don't know how to say that, but you see what they are. So I end up with an answer for k of 0.65. But this part of the problem is fairly standard. Dealing with this kind of stuff takes a little bit of an extra step, so it's just a matter of adding in a little bit of a correction factor there. But that's how you work these slightly more complicated method of initial rates problems.